All right, so today we are doing a note-taking guide on the quantum mechanical model. And so let's talk about the atomic model that we left off with, which was the Bohr model. Right? So in our last class, we did a note-taking guide on the Bohr model. We discussed how the Bohr model worked and all the calculations associated with it. But there's some pretty significant problems with the Bohr model. And any atomic model should explain all matter at the atomic level, right? Because if all matter is composed of atoms, then any atomic model we come up with should explain all matter, right? But there's some pretty significant problems with the Bohr model. The most blatantly glaring one is that it only works for hydrogen. Once you add that second electron in there, it just all falls apart, okay? It is not supported for anything beyond hydrogen. That's a big problem, right? Because there are other elements other than hydrogen. So obviously you need to work on your model if it only works for one element. The second major problem is classical mechanics doesn't support the planetary model, right? Because that's what Bohr model was. You have the little nucleus and these nice, pretty orbits, right? That was the planetary model. Classical mechanics just doesn't support that. There's a significant problem here. So when you're talking about classical mechanics, you're talking about Newtonian physics, right? So it doesn't support this model. The main flaw here is eventually this thing is going to implode, right? Because if these electrons are negative and this is positive nucleus and the mass of the nucleus is significantly greater than the mass of the electron, which it is, eventually this thing's just going to implode, right? Because all these electrons are like, hey, let me get to the nucleus. Let me get there. Let me get there. They're going to just implode. Well, we're still here. We haven't imploded yet. So this model must have some flaws with it. All right. And then there's another major problem. It doesn't explain the mass energy relationship. The mass energy relationship. So think about a stove. If you go home tonight and you turn on your stove and the coil turns red, right? Why is this metal turning red as it gets hot? The quantum model explains this, the Bohr model doesn't. The quantum model accounts for these problems that the Bohr model can't explain, okay? So big problems, doesn't work for anything beyond hydrogen. Classical mechanics doesn't support it anyway, and it doesn't take into effect the relationship between mass and energy, okay? So EXPT is just shorthand for experiment. It's just shorthand for experiment. And I'm summarizing these experiments intensely. Okay, I'm really summarizing these experiments. Summaries of experiments leading to the quantum mechanical model. Okay, energy is quantized. Quantized. What does that mean? It means it comes in packets, so little tiny packets. Okay, energy is quantized. It comes in little packets that we call photons. So light behaves like matter. We talked about this as part of the Bohr model. So energy is quantized. That discovery came from Planck's experiments with black body radiation. And then light behaves like matter, which we call photons. That comes from Einstein and the photoelectric effect. Okay, so these things were factored into the Bohr model, but the Bohr model doesn't fully integrate the way it needs to. Okay, there's another thing that's factored into the Bohr model, but is still leaving some holes, and that is photons. I left out my verb. Photons are emitted. When I typed it out and then I just made myself a blank, left off the verb. Photons are emitted when an electron changes orbit. Okay, that's all part of Bohr's model. So these things are all part of Bohr's model, but they weren't integrated as fully as they needed to be. Okay, so energy is quantized, comes in packets. Light behaves like matter. Photons are emitted when an electron changes orbit. And then all matter travels in waves. So that's from the de Broglie, that was the scientist's name, and the electron diffraction experiment is the experiment that led to that. And then the last one, mass and energy are equivalent. Particles have wavelength and photons have momentum. And that's Einstein and de Broglie together. Okay, so energy is quantized, light behaves like matter, photons are emitted when we change orbits. And remember we learned on Friday how to calculate the wavelength and the color and all that. All matter travels in waves and the mass and energy are equivalent. And I mentioned this on Friday, right? You have a wavelength, right? And then you would also have momentum. Someone picked up, did through you. Your behavior is going to behave more like a particle than it would like an electron because your mass is much, much greater than your wavelength in terms of how it influences your behavior in terms of physics. But nonetheless, you do have a wavelength because you exist. All right, let's scroll down. Let's talk about concepts in the quantum model. So we are just going to talk about concepts. We are not going to do any of the calculations for quantum model. Number one, because this isn't quantum mechanics, and number two, because half the people in the class don't have the math background to do that. So, Calc 3 is a prerequisite for quantum mechanics, just FYI. So this is a math-based model. It's a math-based model. So until you've taken Calc 3, you're not really ready to take quantum mechanics yet. The quantum mechanical model is based on solutions to the wave function. Okay? Wave function is one word, based on solutions to the wave function. And those give us an area in 3D space called an orbital. So we're stealing some terminology from the Bohr model, right? In the Bohr model, we have our little, we called all of these orbitals. Yes, well, we're using that same terminology here. So get rid of the Bohr model. Now we're using the word orbital to describe an area in space. And particularly, what is an orbital in the quantum mechanical model? It is an area in 3D space. So we're talking about X, Y, Z coordinates. All right, so think about your polar coordinates, those of you. Don't do polar coordinates, still Calc 3. Never mind. So just think about three systems, right? Area in 3D space in X, Y, Z coordinates where it is most likely that you will find an electron. Right? So it's called the probability distribution function. So think about it like this. Go home tonight and stare at a ceiling fan, right? You're really bored. You're laying on your couch at ground state, staring at the ceiling fan, right? Okay, where is it most likely that you'll find a blade? You can put your hand right here, where there's no blade spinning, right? It's very, very unlikely you'll find a blade there unless the blade breaks and goes shooting off, right? Stick your hand in the path of that circle, and now it's highly likely that you're going to find the blade, right? You're going to get whacked. So you can think of it that way, right? That path that you see, right? That's the area in 3D space where it's most likely that you will find a propeller blade, a fan blade. Is it probable to find it somewhere else? Yeah, I mean, because if it breaks and goes shooting off, obviously that is possible. Is it likely? That depends on the status of your fan and how damaged it is. But assuming that nothing's wrong with it, right? It's not very likely that you're going to find one anywhere else, right? So you can think of that as the equivalent to an orbital. Or think about, I think your textbook uses apples underneath the tree. So if you have an apple tree, there's most apples directly underneath, and then 5 miles away, is it likely that you could have an apple? Sure, but not very likely, right? So the area in three-dimensional space where it's most likely that you will find an electron. We don't know exact coordinates in terms of my electron is here, in this exact spot, right? We can't say that. But we say it's in this general area, okay? It's in this general area. I can't say exactly precisely where it is, but I can give you the area where it is highly likely to be. Okay, that's why it's called the probability distribution function. Does everybody understand how orbital, that word, differs from how we used it in Bohr's model? Bohr's model called it this nice little circular path, right, which doesn't exist. We say, nope, that doesn't work. We have an area where it's most likely. I can't tell you exactly where it is, but I can tell you where it's highly likely to be, right? And then by converse, where it's highly likely not to be. So again, we're not going to do any of the calculations. We're just going to talk about concepts in the quantum model. And maybe you did this in high school, Kim. Maybe you didn't. I don't know. I guess it just depends on where you went and what level your teacher did this. So we're going to do quantum numbers. Okay, there are 4 quantum numbers. All right, so should have put a spot for name. So let's do, because I can. Thinking about this going, why am I writing on the board? I should have given you a spot for name. There we go. So you can just kind of squeeze it into yours. Need more. Okay, so the first letter is called N, lowercase n. It is called the principal quantum number. And I'm just going to tell you right now, I probably did not give you enough space on the bottom of your handout here to fit all this. So you're probably going to need to go onto the back, just FYI. That's why I left the back blank, because you're probably going to run out of room here pretty quickly. And it's called the principal quantum number. It describes the size of the orbital. Okay. N. Now for shape, you can just omit this one. It doesn't apply to N. And then the allowed values, N can be any whole number greater than 0. Not greater than or equal to, greater than 0. Okay? Why? Because can you have a circle with a radius of 0? No, that wouldn't exist, right? So if the size is 0, and that's a bad analogy, right? Because there is a size 0 in clothes, but let's just ignore that for now, right? You can't draw a circle with a radius of 0. So if there's a circle with a radius of 0, it doesn't exist. So therefore, n can be any number greater than or 0, and not greater than or equal to, just greater than. And then it needs to be a whole number. Okay? No halves. All right. So N. The next one is L. That's lowercase cursive L. I write it in cursive so you don't think I'm drawing a number 1. Right? That's a lowercase cursive L. I just write it in cursive so that you don't think that it's the number 1. That is the angular momentum. Quantum number. Okay, this describes the shape of an orbital. And then this is really, I think you just put a note, C table. We're going to make a table to fit inside this part right here. So maybe write that on the back. And then the allowed values here, allowed value, well actually let's just go through the rest of the table first. Should I do the rest of the table first? Yeah, let's go ahead and do our table while we're talking about shape. So you might want to do this on the back, because we're going to go through all the different shapes associated with each value of L. Let's just go the allowed values here real quick before we go on to the back. This can be any number. Max value is n minus 1. Okay, the max value that's allowed is n minus 1. We're going to go through several examples here in a minute. But now let's go through our shapes table. All right, so here's L, and then here is the letter. So when L is 0, I don't know why I wrote that up so high. I guess I just was trying to give myself space. When L equals 0, that is called an s orbital. And it looks like a sphere. Okay, looks like a sphere. And let's go ahead and make another one, number of orientations. So, a sphere, let's think about this. Maybe you've had, I don't know how far you are in Calc 1, but you probably are not going to be doing this in Calc 1. You have a three-dimensional graph, which you don't do until Calc 3, but you rotate this. You can rotate this an infinite number of ways. Is it always going to look like a sphere? Yes. So how many ways can you orient this in space? Well, there's two answers. There's infinity, or there's just one, right? Because no matter how you rotate this, it's always going to look the same. So there's only one orientation that's possible. Because no matter how you take this and orient it, rotate it, right, it's always going to look the same. So that's s orbital. If I write right here, can you guys in the back still see okay? If I start writing too low, just shout out. Okay, when L equals 1, that's called a p orbital. That's lowercase. These are all lowercase, by the way. And it looks like a figure 8 or infinity or like a dumbbell, depending on how you draw it. So there are three orientations of a p orbital, and I'll show you why. X, Y, Z, X, Y, Z, X, Y, Z. You can orient a p orbital. A p orbital has one node. So you can orient it along the X. You can orient it along the Z. Or you can orient it along the Y. Right? It has one node. Right? That's your node right there. So there are three orientations. So this would be PX, this would be PZ, and this would be PY. Does this help explain why there's only one orientation for sphere? Right? Because whether or not you orient it along X, Y, or Z, it's still going to look the same. But here, because of that one node, you orient it along the X, you orient it along the Y, you orient it along the Z, that is slightly different shapes. And remember, these are solutions to the wave function that tell you the area where it's most likely that you will find your electron. That's the reason why we're doing all these silly little shapes. A lot of high school students come into Chem 1 and they just despise quantum model because they drew these silly little shapes in high school and they didn't know why they were doing it. Maybe that describes you, right? This is why we're doing it, because it's an area where it's most likely to find your electron. So we're sketching the area in three-dimensional space where it's highly likely to find it. All right. Is everyone okay if I erase? I don't want to write any lower. I think I'll run on board. You definitely wouldn't be able to see past the first row. Okay. So L equals 2. That's a d orbital. And I'll go ahead and tell you there are 5 orientations here. The d orbital starts to get messy. Okay, because it has a shape that looks kind of like this, like a clover leaf. So when you start orienting that, my sketching kind of goes to. And on an exam, I wouldn't make you specify which one you did, just pick one. And then there's one that's in between. There are 4 that look like clover leaves, and then there's a 5th one that looks like a p orbital with a hula hoop. So if I asked you to sketch a d orbital, you just pick one, okay? You just pick one. I'm not going to specify which one. You don't need to commit to memory what the names of them are. There are 4 cloverleaf ones, and then one of them looks like a p orbital with a hula hoop. 5 orientations. And then the last one, L equals 3, is an F orbital. I'm not going to make you sketch it because they are nasty. Okay? You don't have to draw that on a planar sheet of paper. If I can't draw an F orbital accurately on a planar sheet of paper, then you shouldn't have to either. All right, and there are 7 orientations for it. Now, I don't have, wait, yes I do. I was going to say, do I have your textbook? And the answer is, I do. So let's look up what page these are on so that you can have reference to that. Orbitals. 317 is what it's looking like. So you can have some higher quality pictures beyond mine. Let's see, that's just kind of leading up to it. Shapes of atomic orbitals. There we go. So this is still talking about the theory. There we go. Yep, 327. So if you want to make a note to yourself, starting on page 327 in your textbook, you have some nice pictures. There's a 327, kind of goes on to 328 as well. And then just for future reference, let's put this in our notes as well. Where are the quantum numbers listed out? So if you missed something today, that's kind of, yeah, that's page 318 to 319. So today's stuff, while we're got our textbooks open, if you want to make reference to this as well, quantum numbers are page 317 to 319. So if you need to read, or yeah, starting on there. So if you need to go over any of the, if you like to read it for yourself, those are page numbers. All right. Now let's go back to our main chart. So that was our like sub chart, right? Now let's go back to our main chart. So we did N, we've done L. The next one is M sub L. It's called the magnetic quantum number. It describes the orientation. So technically, we've already talked about this one. So your options are either 1, 3, 5, or 7, right? There's either 1 orientation, 3 orientations, 5 orientations, or 7 orientations. Shape doesn't apply here because those are your orientations, right? It's either 1 orientation, 3, 5, or 7. And then the allowed values here. So M sub L has to be between and include from positive L to negative L. From negative L to positive L, that's your range. And then your last one is M sub S. This is called the magnetic spin. What it describes is spin direction. So it's either clockwise or counterclockwise. Again, it doesn't really have anything to deal with shape. You can just say it's spinning clockwise or spinning counterclockwise. And allowed values are plus or minus 1/2. Positive 1/2 for spinning one way, negative 1/2 for spinning the other way. That's your only one that's allowed to be a fraction. All your other ones are whole numbers. All right, so now let's go through some quantum numbers, talk about the orbital that it would produce, and then go from there. That's all that I've got on the handout. We're just going to do examples from here with our time remaining. All right, so let's do some examples. I'll give you a quantum number set. You tell me the orbital that it produces, and then we'll go the other way around. Let's actually go the other way around first. For a 3D, actually let's start something simpler. For a 2s orbital, list the valid sets of quantum numbers. More than one set of quantum number could produce the same orbital. So for a 2s orbital, list the valid sets of quantum numbers that would describe it. That describe it or produce it. Okay, the value up here in the front, this is the value of n, and s, that's the value of L, right? We're going to make ourselves some lists of quantum numbers. If we've got a 2s orbital, that means n equals 2. So let's make ourselves a chart. N, L, m sub L, m sub s. Let's list all the sets of quantum numbers that would produce a 2s orbital. So all of them are going to be n equals 2. What's the numeric value for an s orbital? This is something you want to commit to memory. 0, 1, 2, 3, S, P, D, S. Just memorize that. All right, if you've got an s orbital, what's the value of L? 0. All right, what's the range of allowed values for m sub L? It goes from m sub L to positive L to negative L, right? So if L is 0, the only value of m sub L is 0. And then m sub s, what's the possible value of m sub s? There's positive 1/2, so 2, 0, 0, positive 1/2 gives you a 2s orbital. What's the other way that you could get a 2s orbital? Okay. All right, 2, 0, 0, negative 1/2. And if I asked you to sketch it, which I could, what's the shape of an s orbital? Sphere. How would you indicate that it's a 2s? Just count out 2. Right, radius is 2. Make sense? That's how you indicate, because if you draw a sphere and then the person next to you draws a sphere and I'm grading both of them going, is this sphere bigger than this sphere? Like that's way too ambiguous, right? This is very quantitative. And now it doesn't matter how big your scale is, because you can just count out 1, 2, and be done. So there are 2 valid sets of quantum numbers that would produce a 2s orbital. 2, 0, 0, 1/2, 2, 0, 0, negative 1/2. Right? Both of those would produce a 2s orbital. And when we get to electron configurations, right, we'll take this a little bit further. This is ultimately the reason why you do electron configurations. If you did that in high school, you're probably starting to think about that now. Let's go for something a little more advanced this time. Let's do for a 2p orbital. List all the ways that we could come up with a 2p orbital. Okay, the value here at the front is still n. So all of our sets are going to begin with 2. And then this is still the value of L. What's the value of L for a p orbital? 1. So 2, 1. Now what's my range?
-1 and a positive.
-1, and what numbers between -1 and +1? 0. So it's the whole range. So 2, 1, let's just start negative. -1, and then let's do +1/2. All right, that works. But then what also would you have to have? 2, 1, -1, -1/2, right? What else could you do? 2, 1, if this is the range, -1, 0, 1, we have to have that option, right? So 2, 1, 0, +1/2. 2, 1, 0, -1/2. 2, 1, 1, +1/2. 2, 1, 1, -1/2. Does this make sense? Do we see where these numbers came from? So I'm going to put one up on the board for you to try. I'll pause the recording. Oh, we forgot to sketch it. This was 2p, right? Let's sketch a 2p orbital. Now, because we didn't designate which orientation we're dealing with, right? One of them's X, one of them's Y, one of them's Z, so pick your favorite one. I don't really care. Right? 1, 2, 1, 2. There would be your 2p orbital. I just picked Z arbitrarily because I didn't specify which orientation to use. So that means you can pick any orientation you want. All right. You do one. And also sketch it. Let's do 3D. List the valid sets of quantum numbers and sketch. I'll pause the recording. All right, let's go through this one. For a 3D orbital, list the valid sets of quantum numbers. What do I do? That would produce it, and then let's sketch it. So this value here at the front is N. This value here is L. So in all of our sets need to begin with the number 3, right? What's the value of L for 3D? 2. If N equals 3, can L be 2? Is that allowed? Yes, because the maximum value of L is what? N minus 1. Keep that in mind for where we're going next, because next I'm going to give you a set and then ask you, is it forbidden or is it allowed? Right? If these two values equal each other, that would be forbidden, right? Because N and L cannot equal each other. M sub L goes from negative L to positive L, right? Including 0. So 3, 2, do you want to start negative or start positive? Oh, I heard both. So let's just start with the bad, okay? Negative. So 3, 2, -2, +1/2, right? 3, 2, -2, -1/2. Then what? 3, 2, -1. 3, 2, -1. 3, 2, 0. 3, 2, 0, -1/2. 3, 2, what? 1. We're not in a room. 3, 2, 1, -1/2. 3, 2, 2, +1/2. 3, 2, 2, -1/2. If we're drawing a d orbital, I didn't specify which orientation, so you can pick whichever orientation makes you happy. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? Just make sure you scale it so that I know that you know how big this thing is. How do you feel about this? Pretty good. All right. For the next part, I'm going to now give you a set of quantum numbers, and then you decide if that set exists. Is it allowed? Is it legal? And if so, draw it. All right, so for each of the following orbitals / sets, decide if it exists and sketch. If still forbidden, explain why. All right. 2D, does a 2D orbital exist? Yes or no? If so, sketch it. 6S, oops, 6S. Does it exist? Yes or no? And sketch. And 4P, does it exist? Yes or no? And then sketch. And then now here are your sets. And I'm just going to list them with commas, and so you know what's what, right? 5, 3, -4, 1/2. Let's get this whole thing onto a new page. Page break. 4, 2, 0, 1/2, 6, 3, 1, 1. All right, I'm going to pause the recording while you work on that. All right, let's go over these. So for each of these, I'm going to give myself some space here. For each of these, we're going to decide if they exist or if they're forbidden, and then if they do exist, we'll explain why. So 2D, the way to ask yourself if this orbital exists is by just giving yourself the quantum numbers and then asking yourself, is that a legal combination? So N, L, M sub L, M sub S. Let's see how far we get. So this is the value of N, this is the value of L, right? And don't forget our little thing we have to commit to memory, 0, 1, 2, 3, S, P, D, F. Okay, so for N equals 2, and this is a d orbital, so what's the value of L? 2. Is that allowed?
No.
No. Right? Why is this forbidden? Right. Max value of L is N minus 1. Right? If N equals 2, L cannot equal 2. So there's nothing left to do. You don't even need to keep going, because if these two values equal each other, then it's a forbidden combination. So no, does not exist. So if you wrote that as your answer on a test, that'd be perfectly acceptable. And say this orbital does not exist, max value of L cannot exceed N minus 1. All right, let's do this one. Here's the value of N. Here's the value of L. So 6. For an S orbital, what's the value of L? 0. Okay, is 0 an allowed value?
Yeah.
It is, that's allowed. We don't have any minimum value, right? There's not going to be negative though, we know that. So that's okay. So M sub L, M sub S, we could start going through these and start coming up with combinations. But really the thing we need to ask ourselves is this going to be enough to produce an orbital? Because if you know these two, then the rest from here is gravy, right? Because then you could say, okay, so from here, 0, positive, minus 1/2, right? You can finish the rest of it out. But really, these are the only two you need to get started to decide, does it exist or does it not exist? So does this exist? Yes, it exists. And what would it look like? A sphere, and how would you indicate the value of N? Let's just count off 6. 1, 2, 3, 4, 5, 6. Not the greatest circle drawer. Just do your best. That one does exist. Any questions on 1 or 2? Feeling okay about those? Let's go on to number 3. Give myself some more space here. Okay, for 4p, here's the value of n, here's the value of L. So N, L, M sub L, M sub S truly aren't necessary. As long as these two are kosher, we could probably work the rest out from there. N equals 4. What's the value of L if it's a p orbital? 1. If n equals 4, can L be 1?
Yeah.
Yes, because the max value here would be 3. So any number, 0, 1, 2, or 3 would be okay. And the max number beyond that would be in trouble. All right, so M sub L, can we come up with some values of M sub L that would make this illegal? Or what are our values? Let's just list them out. It ranges from negative L to positive L. So, right, you can say negative 1, 0, and 1, right? And then just do your combinatorics, plus or minus 1/2. So is this 4p orbital, does it exist?
Yeah.
Yes, it exists. And what would it look like?
Figure 8-ish.
Figure 8. And then I didn't designate which axis to orient it along, so just pick one. Count off. Do we agree on this one? 4p. All right, for the next one, I've given you a set, and then you decide, is it legal or not? If it is legal, what does it produce? Boy, I hate that cursor being in my face. It just drives me bonkers. I'm going to make these bigger so we can kind of write on them. N, L, M sub L, M sub S. So our first combination was 5, 3, negative 4, 1/2. Let's go through our values. This can be any number as long as it's not 0. This can be any number, what? Maximum value is n minus 1. This has to fall into the range of what? Negative L to positive L. And then this must be plus or minus 1/2. So let's just ask ourselves, are each of these values allowed? If n is 3, if n is 5, can L be 3?
Yeah.
Yes, that's allowed. If L is 3, can M sub L be negative 4?
No.
No, that's where we got into trouble. This would be allowed. This one's not allowed. Right, so no orbital exists for this combination. What would your justification be? If you were doing this on a test, what would you say? Okay, so yeah, negative 4 is outside negative L to positive L. I'd accept that. All right, let's do the next one. 4, 2, 0, that's negative 1/2. Okay, if n is 4, can L be 2?
Yes.
Yes, that's allowed. If L is 2, can M sub L be 0?
Yeah.
Yes, that's allowed. And then if these 3 exist, can this be negative 1/2?
Yeah.
Mm-hmm. What orbital does that produce? It produces what?
It's like clover.
4D, right. So I didn't specify how to orient it. So just pick an orientation. If you had done the version that looks like this with the hula hoop, would that be acceptable?
Yeah.
Yes, it would, as long as you counted off 4. And then the last one, 6, 3, 1, 1. If n is 6, can L be 3?
Yeah.
Yes. If L is 3, can M sub L be 1? What about this?
No.
No orbital.
M sub S must be plus or minus.
Right. M sub S equals plus or minus 1/2. All right. Questions? How do we feel about this?
Pretty good
Again, what's the reason why we're doing this?
for electron configuration.
Well, that's leading us to electron configurations. Why are we drawing these goofy little shapes? These shapes tell us what?
Where an electron might
The area where it's most likely that we'll find our electron, right? And these numbers, why are we writing out these numbers? Just for fun?
they mean something.
They define this orbital, right? They mean something, yes. They define this orbital. These are solutions to the wave function, boiled down, right? That's what we get. How do we get this shape? By these coordinates. All right, that's where we'll stop for today.
Do we not have any exam over this material?
This material